Welcome to Mrs. Z's Chemistry. In this lesson, we will learn more about ionic bonds and covalent bonds. Metals lose electrons to become positively charged ions called cations. Nonmetals gain electrons to fill their last shell of electrons and become negatively charged ions called anions. Atoms want to have full valence shells just like the noble gases, so that is why they will either lose or gain one or more electrons. In ionic bonds, one atom transfers one or more electrons to another atom. These atoms are oppositely charged and are held together with this electrostatic force. We do not call ionic compounds molecules because we don't have a discrete unit that is one ionic compound. Instead, ionic compounds are in a lattice structure, alternating positive, negative through every row and column of the structure. We often call the structure of ionic compounds crystalline lattice structures. These bonds are very strong, requiring lots of energy to break, so they tend to have very high melting points and boiling points. For reasons we'll discuss later, ionic bonds easily dissolve in water. Solid neutral sodium metal is a soft metal. It's soft enough to cut with a butter knife. It is dull grayish in color and reacts violently with water. Even though your hand may feel dry to you, there are still water molecules on the palm of your hand that sodium will react with, burning your hand, as this is a very exothermic reaction. We have to keep sodium metal surrounded in a container of oil so that it does not react with the water anywhere in the atmosphere or on your hands. Diatomic chlorine is a gas at room temperature. It reacts with water in your body and creates corrosive acids, which can do a lot of damage to you. Chlorine has a lot of industrial uses today, but was once used in chemical warfare and World War I. When one electron from sodium is transferred to chlorine, however, sodium chloride, which we know as table salt, is created. This is not only not harmful, but our bodies need sodium ions and chloride ions in many different chemical reactions. Because ions are made up of electrically charged particles, they can conduct electricity depending on their state of matter. Solids can't conduct electricity because the particles are stuck in their lattice structures and can't move. We need freely moving ions or electrons in order to conduct electricity. Ionic compounds dissolved in water conducts electricity as the ions are free to move around in the water. This is why we need to get out of the pool during lightning storms and why we don't use electrical equipment in the bath or near a sink filled with water. Water always has ions dissolved in it. Even in filtered water, there are still many ions, which is why water easily conducts electricity. If you were to melt your dry salt into a liquid by bringing it to a super high temperature, liquid or molten salt conducts electricity because the ions are free to move. I'm saying the word molten because liquid salt is very different than just salt dissolved in water. If you were to pour dry salt into a pan and place it on your stove and turn on high, you couldn't get it hot enough to melt. Your pan would burn first, and you may start a fire before the ionic bonds of the salt could break and turn into a liquid. Please don't try this at home. Speaking of salt, any ionic compound is called a salt. To a chemist, sodium chloride isn't the only salt there is. Ionic compounds are often called ionic salts. Salts must have a neutral compound when bonded together. Use the swap and drop trick to form neutral compounds with each of these elements. Let's find the charges by looking at the periodic table for each of these elements. Magnesium has a 2+ charge. Chlorine has a -1 charge. We can see that we need 2 chlorines in order to make a neutral compound between these two elements. If we were to swap the numbers of the charges and drop them into subscripts by putting a 1 on the magnesium and a 2 on the chlorine, we have a neutral compound between magnesium and chlorine. This doesn't mean the chlorine has a charge of 2. That would be silly. Chlorine can only make a charge of -1. But this 2 now does not mean a charge. It means you have 2 chlorine atoms in this compound. Sodium is a +1. Fluorine is a -1. One of each makes a neutral compound. Potassium has a +1 charge, nitrogen a 3-. We need 3 potassiums and 1 nitrogen then to make a neutral compound. Calcium is a 2+, phosphorus a 3-. Therefore, we need 3 calciums and 2 phosphoruses to make a neutral compound. When atoms become ions, they either gain or lose electrons. Electron configurations of ions will show what subshell and energy level the electron was either added to or taken from. Let's write the electron configuration for each of these ions. For magnesium, let's start out by writing a neutral electron configuration for magnesium. 1s2, 2s2, 2p6, 3s2. This is for neutral magnesium. When magnesium becomes an ion, it loses 2 electrons because it wants to lose its last valence shell that is not complete. So, these last 2 in the 3s2 subshell are lost. This is now the electron configuration for magnesium 2+. Now let's write the electron configuration for a bromine ion when it's neutral, and we're going to do a abbreviated electron configuration. This is the electron configuration for neutral bromine. When bromine becomes an ion, it gains an electron. We cannot put the electron in the 4s subshell as it is already full. Same with the 3d subshell. We have to put this last electron in the 4p subshell. This is now the electron configuration for the ion of bromine. Write the electron configurations for each of the remaining 4 elements. Notice that they are all the same. The only way we can differentiate an electron configuration for an ion versus a neutral atom is you'd have to be given more information, either shown the element symbol or told how many protons this element has. All of these elements, potassium ion, sulfide ion, chloride ion, and phosphide or phosphorus ion, they all want to have the same number of electrons as the nearest noble gas, which happens to be argon for all of them. So all of these will have the same electron configuration as argon. Let's look at a few concept questions. Are anions larger or smaller than their neutral atom? Well, anions gain electrons, and when they have gained electrons, those electrons move into the outer or valence shell. Now this atom has more electrons than it does protons, therefore there are now more electron repulsions between all of the electrons. The electrons repel each other as they all have negative charges. Therefore, this last valence shell is going to expand or spread out a little bit to make room for the repelling electrons. Therefore, anions are larger than their neutral atom. Cations are smaller than their neutral atom because they lose electrons. And when they lose electrons, they do it specifically to lose the last shell. So cations have lost an entire last electron shell in order to become their cation. So they are smaller than their neutral atom. Think about isotopes from when we learned these back in a previous chapter. Isotopes are simply another version of an atom, so it has the same number of protons, but they have different numbers of neutrons. Neutrons contribute to the mass and are located in the nucleus. Let's take carbon, for example. Let's say we have 2 carbon atoms. They both have 6 protons, because that is what makes it carbon. One carbon atom might have 6 neutrons, and the other one 7 neutrons. The one with 7 neutrons, it does have a little bit more mass, but it does not have a larger atomic radius. Adding neutrons into the nucleus does not change the distance the electron shells are able to move out. So, isotopes are no larger or smaller. They are the same size as normal of just any of the other isotopes of the atom. Transition elements usually only have two valence electrons because of the s electrons are greater than d electrons. So let's look at this example of the electron configuration of iron. This is a neutral atom of iron. Its valence electrons are just in the s subshell. So when iron becomes iron 2 plus, it has lost the valence shell of the 4s2 subshell. And now this is the electron configuration for iron 2 plus. If iron were to lose a third electron, then that would mean we take an electron from the d subshell. So this is what the electron configuration looks like for iron 3 plus. This is favorable for the atom because electrons or atoms, even though they would prefer to have full valence shells or full subshells, a half-filled subshell is also favorable. So having only 5 electrons in the 3d subshell means that the 3d subshell is half-filled. Atoms won't always get to have either half or full subshells, but when it can, it would prefer that because it is more favorable for the atom. Transition element cations always remove the electrons in the highest energy level first, which is why we took the 4s electrons from the iron first before we started taking d electrons. Let's go ahead and write the abbreviated electron configuration for these cations in the transition block. Chromium would start with argon, and let's write the neutral electron configuration for chromium first. 4s2 and then 3d4. Chromium 3 plus needs to lose 3 electrons, so we're going to take electrons from the 4s2 subshell first. Now we have made a chromium 2 plus, but now let's take one more electron from the 3d subshell. There is our electron configuration for chromium 3 plus. Write the abbreviated electron configurations for the remaining ions here. Here are the answers. You can now complete problem set 7.1.